Hello everybody, my name is Dr. Christopher Collison, and today we're going to be talking about the experiment that is called determination of concentration of food dye in sports drink. And the objective is to measure the concentration of a particular food dye in this particular Powerade drink or a similar sports drink, and we will also be looking at the concentration of a particular food dye in this blue sports drink. So how are we going to do that? We're going to use spectrophotometry, and we're now going to talk a little bit about the scientific background and how spectrophotometry works. We're going to be talking about something called the Beer Lambert Law, and we are going to talk about how to build a calibration curve for a known sample of the dyes, blue number 1 and red number 40. Let's take a look. So let's start by talking about the names of the particular technique that we care about. We are talking about spectrophotometry or UV-vis spectroscopy. And the idea here is that we have a sample that we want to shine light through, and we're typically going to have a cell, a cuvette, of about 1 centimeter, exactly 1 centimeter in width, in length, in path length. And the idea is that we come in with a beam of light, and we're going to call the intensity of this beam of light I0, and we're going to have an intensity of that light I that is diminished or attenuated after it has been through the sample. So let's consider a couple of samples for an example, and this would be something like the food dye you saw in the image before, the red color of the sports drink and the blue color of the sports drink. So let's imagine for a second that we have a number of molecules of a particular dye in that solution, and we're going to recognize that as that light passes through, some of to the eye, we might even draw an eye on the other side in here. So we typically represent a light source on the left-hand side and a detector on the right-hand side. So this would be our detector. And we recognize that without the sample in place, the detector or the eye would see a brighter light than with the sample in place. This is kind of like wearing sunglasses, right? When we put our sunglasses on, the world outside looks a little bit darker. So we might call the intensity of the light that passes through, well, we'll call the intensity of that light I sub 1. Now, another thing we're going to recognize is that if we increase the amount of food dye that we put into our sample, so let's suppose we increase the concentration of that food dye, of that food coloring. So now we've got a lot more molecules of that dye in the solution, and if we ran the same experiment with our initial intensity I0 and a second intensity is observed by a detector, that would be I2, we might ask ourselves what this new intensity is, I2, how does that intensity compare with I1? And in fact, we must recognize that the intensity of the light I1 is going to be greater than the intensity of the light I2 because more of the light passes through here. More of the light passes through when we have a lower concentration. A second thing that we have to recognize is that supposing we were to double the length of the cuvette, so maybe now instead of 1 centimeter in length, we would say that that cuvette has a path length now of 2 centimeters. So we start again with our intensity of light I0, and we're going to have the same concentration. So we'll note that the concentration of our dye in these two cells is the same. What we would recognize now is that the intensity of the light, let's call that I3, coming through that path length of 2 centimeters now, that intensity is going to be even less. So in fact, the intensity of the light I2 must be greater than the intensity of the light I3. This is as if we put on a second pair of sunglasses, and lo and behold, the world outside would seem even darker. So we can sum this all up with a particular law, a particular mathematical description, and we're going to call that, or we recognize that that is called the Beer Lambert Law. So how do we get to the Beer Lambert Law? Well, the Beer Lambert Law deals with something called absorption or absorbance. So this is where we want to get to, but on the way we're going to recognize that there's also something called transmission, and it's about how much light gets transmitted through any of these samples. So we're going to start by thinking about transmission. What is transmission? So transmittance or transmission are one and the same thing for the purposes of this introduction. And what we're going to recognize is that when we take the intensity of the light that passes through our sample I1 and we divide that by the initial intensity, what we're going to have is a fraction. It's going to be some percentage, and often we write down a percent transmittance, and if we're working with percent transmittance, we're going to multiply this fraction by 100 in order to get a value that is a percentage term. So what we recognize here is the transmittance. In our first case, we'll call this case A. The transmittance is larger, more of the light passes through than in case B, and more of the light in case B passes through than in the case C. So how is transmittance or transmission related to absorbance? The absorbance is the amount of light that's actually absorbed by the sample, and that's typically what we measure in the lab. So in fact, what we're going to do is bring all these things together, and we're going to, first of all, define our absorbance as being equal to the negative log of the transmittance. So let's think about this for a second. If the transmittance is quite large, that means a lot of the light gets through, then the percentage transmittance is quite high, right? A lot of I1 gets through. Then what happens is, because we've got a large number in here, but we're taking the negative log of this transmittance, then that means that the absorbance is actually quite small. So that makes some sense, right? When more light gets through, the sample itself is absorbing less. So why am I interested in absorbance? Why am I interested in transmittance? So absorbance is defined as the negative log of transmittance, right? So this is also can be written minus log of transmittance T. So why do I care about absorbance? Well, this Beer Lambert law is associated with absorbance, and so the absorbance is proportional to the concentration of the absorbing analyte in our sample, and it's also proportional to the path length that light must pass through. How do we write this mathematically? Well, because of the proportionality in here, we need a constant. So I'm going to rewrite this as a new expression, and this is the Beer Lambert law. So we're going to write this as ECL, where the path length is now L. The concentration is given here as C, and the proportionality constant, we're going to call that is called the molar absorptivity, and that may also be called the extinction coefficient. And these two terms are used interchangeably. So what we recognize now, it makes sense that as we increase the concentration, the absorbance goes up. So the absorbance goes up. More light is absorbed when we increase the concentration. More light is absorbed when we increase the path length. So the only thing left to think about is this molar absorptivity. So what is the molar absorptivity? So this molar absorptivity is an intrinsic property of a particular analyte, of a particular material. So red number 1 has its own intrinsic molar absorptivity, and blue number 40 has its own intrinsic molar absorptivity. Loosely speaking, that molar absorptivity is a measure of the probability that a particular photon will get absorbed by a particular concentration of that particular molecule with a certain path length of travel of that light through the sample. So what we're going to be doing throughout this particular experiment is we're going to be using a graphical approach to calculating the concentration of red number 1 or blue number 40 dyes in these particular sports drinks. So we're going to find that a graph is fairly useful, and in that graph what we're going to plot on the known axis, on the x-axis, is concentration. The units there are going to be in moles per liter. On the y-axis we're going to have absorbance. Now, absorbance is a unitless quantity. There's a log function that's associated with the absorbance, and therefore there are no units. So there are no units to place on the y-axis. But what we of course recognize is when the concentration of our sample is 0, the absorbance is 0. What we find is that as we start to increase our concentration in a controlled way, what we find, because of our proportionality constant, when we plot the concentration, when we know that we can double the concentration, we know that the absorbance is going to double. In all of our experiments in this particular in this particular lab that we're working on, we're going to always have a path length of 1 centimeter. And this means that the absorbance will only change with the concentration. So the good news here is we will have a straight line through these data points. And in a nutshell, when we know the concentration of a standard solution of red number 1 or blue number 40, we can plot a graph like this. We can use a spectrophotometer, we can do some UV vis measurements, and we can start to plot the absorbance as a function of concentration. And at some later point, what we can do is we can take some of our sports drink, we can put that sports drink into our 1 centimeter wide cuvette, we can put that into our spectrophotometer, we can measure the absorbance. Let's say we measure our absorbance here, and that will immediately tell us, if we can measure the absorbance, that will immediately tell us what the concentration is in our unknown. And what we're going to call this line that we're going to generate, we're going to call this a calibration curve. And that, in a nutshell, is how we are going to run this particular experiment and how we are going to determine the concentrations of red number 1 and blue number 40 in our unknown sports drinks. Thank you very much for listening, and good luck with your experiments and calculations.